All right, so how can we scale up Umbrage applications to cloud computing? So ideally, what we would like to achieve is to sort of automatically scale up UQ applications for compute-intensive models. We would like to keep the UQ client, so the software that does the requests and performs async quantification, as simple as possible. We'd like to avoid machine-specific setups for the model. Of course, we would like to massively parallelize models in the sense of parallelization of the forward model itself is not our concern, but in the sense of running independent instances of these forward models so we can parallelize on the statistical level as well. And of course, ideally, the whole thing should be sort of a single point of entry. In other words, we don't want to adapt to specific setups on either UQ or model side. That's a nice wish list. So how can we make it work? We've already seen that we can containerize Umbrage models, which takes away a lot of the technical setup. And essentially that takes our first box. Once we are able to set up container images and we're able to spin them up on our target platforms, there's no installation specific to a certain model, and we can essentially just swap out container images and containers depending on what we want to work on. And then, let's say, simulator versions get updated and so on. So how do we parallelize? Well, we need, first of all, hardware that can do parallel computing. On the one hand, we have traditional high-performance computing systems, supercomputers. Those are typically sort of bare metal machines. There's no virtualization happening, and the operating system just handles separation between users who, well, user management in an established way. But of course, there's a catch that due to these being bare metal machines, they're always a bit peculiar, and you might be restricted in, let's say, compiler versions or versions of certain libraries that are available and so on. And I think those of you who have tried running things on supercomputers are well aware of the sort of technical engineering overhead that this brings, just making applications run on such systems. On the other hand, we have cloud systems. Those are built sort of containers first. In fact, containers were the, let's say, great success of containers actually comes from web services. It's quite clear where this comes from because, well, they need to frequently update versions of pretty complex and interacting um, services, and in particular, they would like to dynamically scale depending on demand. That's where cloud systems originally come from, being able to dynamically adapt to resources without having to essentially buy hardware on peaks and sell it afterwards again. Um, Now, cloud systems are, of course, not really built for scientific applications, or they used to not be built for scientific applications. But over the years, as it turns out, these two worlds are, of course, trying to, let's say, learn from each other and bring together the best from both sides. And to some degree, those worlds are actually converging. We still have the effect that HPC systems are a bit less convenient regarding software, and cloud performance, cloud computing is less performant, tends to be less performant when you have heavy communication between nodes working on a single task. But nevertheless, things are coming closer. In this talk, we are mainly focusing on cloud systems because those have, as I mentioned, container first, a container first approach, basically, which makes it very easy for us to take these containerized simulations that we looked at before and spin them up. So for those unfamiliar, the infrastructure in a cloud system can be roughly and very roughly be categorized into, we've got some network infrastructure connecting server hardware, so really physical computers sitting somewhere in something like a warehouse. Now, because these cloud systems are intended for public cloud in the sense of pretty much anyone can just rent resources, they make heavy use of virtualization, which allows them to very cleanly separate different users of these systems and of course make sure that you can access your neighbor's data, while on the other hand making sure that you can bring your own computing environment. On top of it, we've now seen containers, which are essentially a somewhat lighter weight way to make applications portable. And on top of that hierarchy, inside these containers, we typically have our applications. On the Google Cloud Platform, for example, you find products that essentially give you control over virtual machines. You cannot directly control bare metal computers. After all, that would be a major security concern if you have thousands of users accessing these systems. You can, however, on a higher level, get access to what they call the Kubernetes engine. That gives you access on a level that does not think about virtual machines and surrounding operating systems anymore, but you really only specify what containers you want to run and how they're supposed to interact. That is facilitated, in case of Google, by Kubernetes. And this is in fact open source and widely established, even though I think there are some alternatives. Now, interestingly, on this kind of container orchestration level, we get pretty much reproducible setups regarding how exactly we spin up our software and how we make it interact, which is quite far ahead of what we find with HPC systems, where again, you might find even different compiler versions and might not get the exact same, might not even get the exact same program running on a binary level when you compare different systems. And by the way, just for completeness, you can also get certain offers that do not even handle the level of containers anymore, but it goes all the way to a point where you can essentially write simple functions in a certain very restrictive set of languages with a sort of restricted set of functionality, of course. And it's enough to just plug in source code, which is really cool for some for specific tasks and smaller projects. But in our case, the level that we really want to operate on is containers, because we get to bring our own dependencies, our own languages. That's really what we need for scientific computing. We also don't want to directly operate on virtual machines because, again, we want to get rid of this whole system setup affair. So containers, and in case of Google, Kubernetes engine, it is. Now that ticks the box of running parallel instances, at least regarding hardware. Now, we need to make sure, of course, that we can interact with parallel instances of our simulation codes, and we can manage them. As for management, Kubernetes itself is described as an open source system for automating deployment, scaling, and management of containerized applications. And importantly, this entire setup can be defined in config files. Since we have a very specific demand in parallelizing UQ applications on simulation codes, we actually provide a general purpose Kubernetes configuration alongside with Umbrage, which you just find in the Umbrage repository as well. And this particular configuration essentially describes how we want to run simulation codes and how we want to pass requests for simulation runs between them. We have two versions. One of them is for the case where your simulation model is supposed to run on a single physical compute node. And that's already going to cover a lot of cases. As Anna has already hinted in the previous talk, MPI parallelism across physical nodes is a bit of a challenge with containers, since really MPI was never designed for this kind of environment. So in this case, we have a couple of extra restrictions, but it can be made work as well. So how can we use this with single node models? The overall architecture is pretty simple. On our Kubernetes cluster, the Umbrage Kubernetes configuration spins up a load balancer. It also spins up an arbitrary number of instances of the container, of the image that contains your simulation model. Interestingly, the load balancer and all the surrounding setup is pretty much universal. So all that you need to do is swap out the name of the image later on in order to get a different model. So this really still ticks the box of our simulation model is supposed to be independent of the environment that it runs in, and spinning it up in such a cluster does not require any modification on the model side. And on the client side, the setup still ensures that we are still talking umbrage to the cluster. So the same client that you might use for testing on your laptop with a containerized model or with a bare metal model is still going to work immediately with such a cluster, but the only difference being that, of course, you pointed to the IP address of that cluster. The one major thing that has actually changed is, of course, now that your UQ software may make parallel requests. For example, it may do so in a thread parallel fashion or using whatever parallelization you want to use on your laptop. And these parallel requests will be processed by the load balancer and passed on to individual model instances, ensuring that we are quite literally balancing load across all of these model instances that we have available. In other words, we can rely on very simple parallelization techniques for our UQ client, while the server-side load balancer handles all the work of managing resources and distributing work across the instances that we have. So this finally ticks the third box. We have a single point of entry for UQ and load balancing of tasks or simulation runs, such a cluster. Now, what does it look like in practice? I mentioned that Kubernetes can be controlled through config files. And here's an example of such a config file that is part of our Kubernetes configuration. In fact, it's the most important part for your user. It's the model.yaml file, which essentially just specifies that we would like to spin up a container, in this case named model I2C. We want to give it 1 CPU core and 1 GB of RAM. And of this kind of container, we would actually like to have 4 instances called replicas in the Kubernetes world. And that's pretty much it. So this really spins up 4 instances of that simulation code. And the other config files that we have will handle setting up the load balancer and services around it. Which means that if you actually want to apply this to your own setting, it really comes down to changing the image name to your particular image that you may have uploaded to Docker Hub or made available to that cluster in some other way. Setting the number of model instances that you want to have, and of course, specifying the resources you're going to need. This is really all the modification from our standard setup that you need to do, and you can then apply this on a cluster. What does it work out regarding scalability? Well, with some testing, we've seen that we could easily scale to, in this case, 210 instances of an actual simulation code, connecting or actually driving these simulations through QMC Pi, which is the quasi-Monte Carlo package that we've already used in the tutorial before. And importantly, we have just used QMC Pi's inbuilt parallelism. QMC Pi itself is really only thread parallel. It is not capable of readily just running on a cluster, let alone a cloud cluster. But thanks to the umbrage integration and the cluster-side load balancer, that just works as it is. Now, we get a bit of a bump up here. Well, there's 2 things. On the one hand, QMC Pi is not really, we haven't really optimized any code regarding simulation model and QMC Pi. And on the other hand, of course, there's always a bit of communication overhead going on if you're running multiple instances. So considering the basically non-existent effort for scaling up a QMC Pi application to 200 model instances, I think this is a fairly good result. If you want to do it in a slightly more complex setup, we could also do multi-level methods, for example, by setting up different load balancers for different levels. And we might, of course, as we've shown before, play a bit with microservices in order to make our setups a bit more complex and advanced. But again, we can neatly separate complexity into individual pieces between a UQ code that really just is not aware of the complexity of the surrounding setup, and that we do not have to adapt to the specific application. This Gaussian process emulator here does not know that it's actually talking to a cluster behind the scenes. And again, the model instances themselves are fully portable. And we've demonstrated that we can run such a setup on thousands of CPU cores in order to solve scientific problems and really gain scalability at pretty much no technical overhead. Whereas with a traditional setup, we would spend at least days of optimizing cluster-specific setups, finding out how to spin up tasks on or jobs on a specific cluster and interlinking this with UQ codes and so on. By the way, one particularly nice application that we had was running a MATLAB code with a parallel for loop on a laptop and remote controlling through Umbrage a cluster of Fortran simulation codes. So if you imagine bringing together MATLAB, Fortran, and parallelism on a cluster, this sounds like quite an engineering project, but in this case, it was really just a matter of plugging the components together. All right, I'm now going to go for a very quick demonstration of how you can set this up. On Google Kubernetes Engine, we get access to something that they call Cloud Shell. Essentially, it's kind of similar to an SSH login ultimately onto a virtual machine that is hosted on the Google Cloud system. We now have access to a tool called Kube Control, which is the primary way of interacting with a Kubernetes cluster. Now we would like to, now we have an empty cluster as it stands. And if you ask, for example, for pods, you can, for simplicity, think of this as containers of Kubernetes. It tells us that we don't have any available. However, we can now follow the instructions on the Umbrage tutorial. So let us see for the documentation and Kubernetes section. So the Kubernetes section instructs us to set up a load balancer by performing the following commands. So some of this is going to be redundant in my case because I've already done that on this cluster. These we can really just copy because this is general purpose setups that are not specifically adapted to any particular model that we're running. At this point, we now have a load balancer available, and it is ready to interact with a set of model instances that we can provide. I've shown you before that we have this model.yaml file. In this case, I'm specifying that I would like to have 6 replicas, so 6 instances of a container, which is the Linus Seelinger model L2C benchmark problem from the UQ benchmark library. We specify that we would like to have one CPU core per instance and 1 GB of RAM per instance. Now this describes how our model is supposed to be set up. And this is pretty close to the original model.yaml that you find in our repository. I've only adapted the image, number of instances, and resources a bit to my needs here. I'm now going to apply this. And now you've seen that this has already very quickly created all these containers that we would like to have. So this is now 6 containers, 6 instances of this particular model container that are ready to be called from a client. Finally, we can use another command in order to access an address that we're going to use in the following to interact with the model, and we'll do that during the tutorial. So while this may have been a bit fast, this is really just to show you there's very little work that needs to be done in order to scale up a UQ application on a containerized simulation code using this existing setup. And you can really mostly just copy paste our existing configuration files while only adapting the absolute minimum to your specific case. Quick mention regarding MPI. MPI across containers is necessary if you want to do MPI in a containerized application across physical nodes, since containers are by design restricted to one particular physical computer. Our way to work around this is that we provide a particular base image, or that we make use of a particular base image that supports MPI. And we have a slightly adapted Kubernetes configuration that allows you to now have MPI launchers and MPI workers, much like you would have it on a traditional HPC system. And in addition, you get an NFS server for a shared file system. The outcome is that your simulation code instances will see an environment which is very similar to what you find on a traditional HPC system, with API support and with a shared file system to write intermediate results to. Again, there are some minor restrictions, but in general, we get the same architecture as with the simpler case. All right, so wrapping up, with this Kubernetes setup, we do not have any model-specific setup happening. Again, you can just use container images. There's no installation in that sense happening on the cluster, and you're guaranteed that you get the same output compared to what you're running on your own system. We provide reusable configurations, which require minimal adaptation to support different models and different scales. Any Umbrage client can interact with such a cluster, and parallelization is pretty simple. In particular, the way that you parallelize your UQ software is now fully independent of how you distribute tasks on the cluster or how the model itself is parallelized, which means a lot of UQ packages will readily work with this setup. And finally, and this is leading over to a chunks talk now, we have a very similar setup that also works for HPC systems, even though, of course, it's a different world, but importantly, from the UQ side, it's going to look similar.